My name is Robert Terry, and this is my final project tutorial, Spark Streaming as a Platform for Internet of Things. IoT device use has exploded in the last few years, and it's going to continue to grow. Data is being produced in vast quantities unheard of just a few years ago. Megabytes and gigabytes are quickly being replaced in our vocabulary by terabytes, petabytes, and even exabytes. Processing this data in real time and filtering through the noise to find nuggets of useful information is a challenge. My project was building a basic Internet of Things message filtering application that uses Amazon Kinesis and Spark Streaming. It runs on an EC2 cluster with a master and 4 workers. Filtered messages are queued for further processing in SQS. Amazon Web Services software development kit for Python Boto is used extensively, as well as other various AWS services. To task my application, I needed a large ioT source, so I built an ioT message simulator written in Python and using Boto 3. It creates 2,000 to 3,000 messages a second, which is about 5 to 6 million messages in an hour. I wanted to see how well Spark and Amazon Kinesis kept up with that large data stream. Something I discovered as I was going through this project is how easy it is to provision resources using the software development kit for Python. And what we'll do in this tutorial is basically provision every resource we need with Python code, as opposed to having to go through the Amazon Web Console. This can also be done with the AWS command line interface, but with Python it's pretty simple, it's pretty clean, and it's pretty easy. There's a couple of assumptions I'm going to make here, and I'm going to limit the scope of what I go through. I'm not going to explain how to set up an Amazon Web Services account. There's plenty of tutorials on the web for that are better, and that's a certain assumption that I'm going to make that you know how to do this. I'm also not going to go through how to create your secret keys, how to secure shell into a remote server, because again, that's kind of taken for granted, and there's various softwares to do that depending on what platform you're on. Finally, I'm going to assume that Spark is installed on your virtual machine or Amazon machine image or whatever you're doing. We're not going to go through how to install Spark. We've done that in earlier class lessons, and there's pretty good tutorials on that. As a matter of note, the version of Spark I'm using is the one that we've used pretty much from Homework 2 or 3. I've been using it on an Amazon machine image since Homework 5, and so this is really no different version of Spark than anything we've used in all of our classes. It's been upgraded a little bit. I installed Boto 3 on there, and that's just a simple sudo pip install or whatever version of Linux you're using to install that. Here's a quick schematic of my app. We have the ioT simulator here, and that's running on Python. It creates, like I said, a few thousand messages a second and dumps them into the Amazon Kinesis stream. The way the stream is configured, it will hold messages for 24 hours, and it can be read by multiple applications. Spark Master reads the stream, and it runs my Spark program, which we'll look at later, sends the information out to 3 workers who filter it. You need a database, and this is created pretty much, I think it's created automatically, and it's Spark uses that to keep its place in the stream here, so that if it's stopped and started, it knows where to start again. The Spark Master takes the thousands of messages, and it's looking for a certain criteria. And let me go back and talk about my made-up scenario. So since I've created this Internet of Things simulator, my scenario, and we'll come back here, is essentially a courier service running, working in the state of Massachusetts. So you've got vehicles all over the state. They send telemetry data back to the Amazon Kinesis stream on a second-by-second basis. There's also customers who can request package pickups, and this sends Internet of Things messages back as well to the stream. A sample message for the courier would be the timestamp longitude, latitude, the courier ID, the topic, and the topic for the couriers is all MA for Massachusetts courier, and then telemetry, the current speed, and equipment status, which varies from OK to 1, 2, or 3. If a customer is sending a message using their device, it notes whether they're paying cash, their ID, the topic, Massachusetts customer pickup, how many packages do they want, their location, and the timestamp. And the goal is to filter through all of this in real time and extract useful information, i.e. which couriers have maintenance issues, and then we pass that off to another program which isn't created at this point in time to act on that. Let me go back again to my schematic. We pull out certain information and store it in an S3 bucket, and the visualization web page pulls that information out, and then we can look at that. And I said finally, I don't know if I've covered this or not, we write messages to Amazon Simple Queue service, and we can look at those, but in our scenario, those are acted upon by another program. Pretty much all of this is provisioned using Python and Boto, although we're going to go over in a few seconds the basic groundwork that needs to be set in AWS as far as credentials before you can do that. Okay, the technologies. We're going to use Jupyter with Boto installed. Python 3 is running in Jupyter, and then Python 2 is running on my Linux instance up in the cloud, and that's Ubuntu 16 running on that. The AWS cloud services are Kinesis, EC2, S3, SQS, and DynamoDB. You could probably do this on any cloud service. I'm not too familiar with the other ones, but they all seem to pretty much offer the same services. Spark Streaming, we're using version 2.2. We used Kafka in class, but I wanted to use I wanted to try Kinesis because I'd been reading about it. So to allow Kinesis to talk to Spark, there's a utility or a module that you have to install. Kinesis utils and initial position and stream, and this is from the module pyspark.streaming.kinesis, so that's needed as well. As I said, Ubuntu 3 is used for the instances, and then I use D3 Plus for the visualization. Okay, so first thing we have to do is set up our users in Amazon, and I said ideally you already have an Amazon account, so this is just showing you the basic rights I needed for both my local version running on Python and then for Spark. And these are set up two different ways. Locally, I'm using environmental variables with a user with certain rights, and this is when I'm running my Python program to provision all of those Amazon services we saw, and then to run my Internet of Things. So the user is CLI, and these are the permissions that are needed. You need full access to the DynamoDB, you need EC2 full access, you need EC2 spot fleet role, and that's because I'm saving money, so I'm using running these as spot instances as opposed to paying the actual going rate, and you save quite a bit of money that way. The EC2 spot fleet tagging role, S3 full service, Kinesis full service, Kinesis Firehose. I don't believe you need that, but that was added on when I was trying something differently, and then the Simple Queue service full access. And a lot of these are accomplished by them being in groups, but the permissions pretty much covers everything you need to run the Jupyter Notebook, to provision, and to start the Internet of Things. Now roles, this works great for the Spark streaming engine. When we fire up an EC2 instance, we can assign a role to it, and basically it gives the programs running in that instance, the way I understand it, these rights. So I've created a role. It's E63 EC2 S3 access. but actually it's more than S3 access. So, okay, this role is going to be, and we'll talk about it more, but this essentially, this role is married up to the EC2 instances that are fired up. And so just these four policies: SQS full access, S3 full access, DynamoDB full access, and Amazon Kinesis full access. So essentially that's everything that the Spark program is accessing while it's running in the cloud. Okay, so now that we've covered that, one last thing, and then we'll start going through the code. The program we used in, or the book we used in class, the Spark book, talks about what you have to do to set up Spark. And I found that parts of this worked, parts didn't work. I got on the internet, some things worked, some things didn't work, and I ended up having to kind of develop my own process because I'm running Spark as a cluster. I'm running a master, and I'm going to run, in this case, 3 workers. We didn't do that in class. All we ran was the master locally. Okay, so now I'm running the master in the cloud, and I'm having to control 3 workers. And ideally, there's code that comes with this. I wasn't very successful. But what you do have to do on the master is you have to create, and this is on page, looks like 130 of our book, Learning Spark. You have to run this code, which basically creates a public key, private key. You save it, leave the passphrases empty, and then on the workers, you do the same thing. You create that, and then you save this in the same directory, the home directory, the hidden directory, SSH, and in that file right there. Okay, so essentially step 2, if you do this, then it allows the master and the slaves or the workers to talk back and forth to each other. The rest of this I wasn't too successful as far as the start all and the stop all. Parts of it would start, parts of it wouldn't. So what I eventually ended up doing is going into each worker and starting it manually to talk to the Spark engine. Now this obviously wouldn't work for a larger cluster, but for my cluster of 3, it's a workaround and everything works great after that. And this is actually what I did. If you look down on step 5 here, talking about starting it manually. And we'll talk about that more in depth. Okay, so now that we have our configuration set up and our rights, and okay, actually there's one more right that I forgot about. If we go to EC2, which is our Elastic Compute 2, I believe that's what it stands for, we have to set up our security group. And to make things easy, I don't normally do this, but I use the security group where everything is wide open. And that way the master and the workers could talk back and forth to each other. I didn't have to worry about things not working because ports were blocked off. And so I'm using this security group called Open to All, appropriately named. And if you look at the inbound, essentially there's no filtering, there's no blocking. Normally, I've got ports blocked and I'm only using them in wherever I'm located. But in this instance, just to keep things easier, I want everything wide open. Now, if you're going into production or you had it working and you wanted to start tightening it down, then I would start closing up ports and seeing what was needed and what wasn't needed. But for today's purposes and for the purposes of this project, that's the easiest thing to do, is just keep everything wide open and go from there. Okay, so now that we've got that in place, let's go over to Jupyter Notebook and take a look. We're running Python 3 code locally. It's Python 2 in the cloud, but on my MacBook, it's Python 3. pip3 needs to be installed. If you haven't installed it, you can actually do it right in Jupyter Notebook using a magic command. That's !pip3 install Boto 3. Everything that's running here in Jupyter is running from my AWS configuration file, and that's my home directory, hidden directory, AWS config. And again, that's outside the scope of how we're going to, what I'm going to cover here, but those are the environmental variables that it's pulling the rights from. I'm running in the US2 East Ohio region, and the libraries I'm going to use for this are Boto3, JSON, NumPy, random. I use time, I use threading, I use math. This program, Kinesis Create Stream, does a couple of things. It provisions everything. It also creates the Internet of Things simulator, which does the 3,000 messages a second. And then when everything's done, there's also 3 or 4 cells of code to break down all the provisioning. So this is so much easier than going through the web page and going from EC2 to Kinesis to SQS and deleting everything. I can do it all here, and it's done in probably less than a minute. So let's go ahead and import our libraries. And while that's going through, I have all my constants up here. Number of Spark workers, I have 3. And what's going to happen is it's going to start 4 instances. So I have 3 workers there. I'll start those 3 plus the master. For the number of couriers I'm simulating, I've got 4,000 here. So each of those, a fraction of those, say 30%, give or take, and there's a lot of randomization here so that it's not just cranking out numbers, but more like real-time messaging. A fraction of those will send out messages every second. I've got 15,000 customers, and a very small fraction of those will be sending pickup requests every second. And then the boundaries for the geotagging, which is essentially a square box around the state of Massachusetts, and then a little bit of extra boundary, and then a speed range of 15 to 55 miles an hour. Let's make sure I run this before I get on to the next. So Spark uses the AWS DynamoDB to keep track of where it is in the Kinesis stream, so that if it's stopped and started, from what my understanding is, it looks in the table and picks it up where it's left off. That's great, but the problem is if you're doing like I'm doing and you're stopping numerous times, the table has to be associated with the current Kinesis stream. So if you have a table, but it's from a previous stream, it doesn't like that, and then it throws an error. So I delete this table several places just to clean up, and that way I'm ensured that when it's running, it's not going to throw an error. Okay, so this is the first place we're going to use the software development kit Boto3 code. The table name is ioT prototype, and what we'll see, and it's the same pattern for every resource that we create in AWS using Boto3. We have the Boto3.client, and then the name of the resource we're going to create, and then we assign that to an object name. So I keep it pretty simple. This is a database, so it's DB client, and then we're doing DynamoDB, so we're creating that object. They also have this great resource that's waiters, and what you can do is use them, and it will wait. It polls in the background until the case is met. In this case, it's waiting for the table not existing. Okay, so it tries to delete the table, and it's waiting until the table is deleted, and it'll try 7 times, or 15 times with 7-second delays. And if it's successful, it'll say previous table deleted. So that's great. If the table doesn't exist, and that's my exception, then it'll say the table's been previously deleted. In this case, I think I deleted it when I cleaned up last time, so that's not going to be an issue. It'll say table previously deleted. But the waiter's real nice, and if you start using the software development kit, I recommend using that. So now we start setting up the infrastructure. We've cleaned up everything. We should have a blank slate. So we're using SQS Simple Queue Service to pass messages from Spark back to the ioT devices. Now that's not really happening. What's happening is they're going in the queue, and ideally another app that in our scenario would pick them out of the queue and then route them to the correct devices. But we've got to create the queue. So we're going to do it here, and that way all our setup is in one place. We've also got to create a spot instant request. I use spot instances all the time because you get a lot of performance, you save a lot of money. What we're using, or what I'm going to use today, is it's an R4 large, I believe. The specs, you have 2 virtual CPUs, a little over 15 gigabytes of memory. you can usually get it for about 1.6 cents an hour, and I think that's charged to the minute. So I bid about 3 cents an hour. I've never been terminated. If I was, since I'm not doing anything in production, it's not a big deal, but it works out pretty well. So this is going to cost me about 6+ cents an hour just for the EC2 instances. And so the same scenario as above. We create a client. It's an EC2 spot client, an EC2. And what we have to do is put in our configuration, just like if we were on the web page. So it's there's 1,000. It's kind of overwhelming the first time you've done it, or the first few times you do it, and because there's 1,000 options here. But depending on how customizing you are, you don't need most of them. So first of all, the security group, we looked at that, open to all. EBS optimized, I think that's just something that makes you get quicker response between the storage and the actual instance. The IAM profile, this is what we looked at before, the roles, so that they're attached to this instance, or these instances, so that the programs running on this have access, in our case, to S3, to DB3, to SQS. And there it is, the E-63 EC2 S3 access. The image I want to use, which is, like I said, a Ubuntu image. It's got Spark 2.2 that I used for all the exercises from homework 5 onward. It's an R4 large image. I'm running it in the Ohio. Oh, actually, this is a key name. So this is the key name that I have for my public key, private key, that lets me secure shell into the instance. Placement, I'm using US East 2C, which is in Ohio, and I'm using 2C. I specify that because I've got a volume that I use that I keep all my work on, and that persists even after the instances have gone. So if I have to launch it in that same availability zone so that I can attach the volume to it and get my programs off of it. The spot price, I'm bidding a whole 3 cents American. It's a one-time bid, and if the instance is interrupted, we want it to terminate. And then what we're going to do is we're going to print out what happens after we put in the spot request and the information we get back from Amazon. Okay, a whole lot of information here. We don't really need any of it. I'm going to try to pick some out. The nice thing about this is if you're using this to bootstrap on to another program or something, you can pick out, it's looks like dictionary, and there's JSON in there. For instance, here's the key name. It's in Ohio. We bid it in US2 East. There's the machine image and the instance type, which is an R4 large. There's our price. That's the create time. And all this is for the request. You've said, hey, give me 4 instances. I'll pay 3 cents for each of these instances. Okay. Now, because we have 4 instances running, I want to keep track of which one is the master and which ones are the workers, because I need to secure shell into the master, and then at times I need to start Spark on the workers, and then I'm pretty much done with them. But it's easier if we can see, and let me refresh this. So right now we've got 4 instances running, but they all look the same. So what we're going to do is we're going to tag them with the name master and workers, and this gets the information out of there, and it just goes through and it tags the first one with master, and then all the remaining ones with the word worker. So now, one is designated the master, the rest of them are the workers. All of these instances right now are identical, so it doesn't really matter which is which. They're all running the exact same instance type. They're all running the same Amazon machine image. They all have the same specs. Okay, so while those are spooling up, we're going to go ahead and we're going to create our SQSQ. Now, this isn't going to be a factor here, but you've got to wait like 60+ seconds as after you create the queue before sending messages. That's not going to happen because it's going to take us another 5 or 10 minutes to actually get Spark fired up and firing off messages, but that's just something to keep in mind. Okay, so again, the same nomenclature. SQS client is the object name, and we're assigning it's a Boto3.client, and in this case it's SQS. I really like the Boto3 API, and I also like the documentation. It's pretty easy. It's pretty straightforward. It's one of the better documentations that I've seen. It's one of the easier APIs that I've dealt with. And all you have to do is Google Boto3 or Boto3 documentation. Okay, so we're going to make a queue, and it's a first in, first out queue. Why are we using that? Well, that, from my understanding, it helps prevent message duplication. We'll just leave it at that for now, but that's why it's called ioT queue.FIFO. And again, just like before, we're telling it some basic information. We're going to say, hey, SQS client, which is the object we created up here, create this queue, give it the queue name, which is ioT FIFO, and then here's a bunch of attributes for this queue. Like the message retention period is going to be 2 hours. It's a FIFO queue. It's true, and a couple of other things that I'm not going to get into here. We can go into the Boto documentation and look up. And like I said, there's 1,000 different options. This is just the basic bread and butter queue to get it up and running. If it throws an exception, so we try, if it throws an exception that the queue exists, it's just going to tell us the queue already exists, and that's going to be that. Otherwise, it's going to print the response, and we're going to get the queue name out of there, and it's going to print us the queue URL. And this queue actually, we get a response pretty quickly. It's not usable for 60 seconds, but we get a response, and we see what the queue URL is, which is essentially the region we're in, queue, a number, and then the queue name. Okay. We're going to stop here at this point, and we're going to secure shell into the EC2 instances to set up the Spark master and the workers, and then we're going to come down and create the Kinesis stream. So let's go over there. Now the first thing we need to secure shell into the Spark master is the IP address. You can either use the public DNS name or the public IP address. A lot of people, and if you look at a lot of tutorials that say use the public DNS name, I don't know what the difference is, and 99% of the time I use the public IP address because honestly it's shorter. Just be careful that you don't come down here and grab the private IP address or the private DNS name, because you're not going to get anywhere if you do that. So I double click on it, I control or command C to copy it, and I've got a script that helps me secure shell because I do this fairly often, and depending upon which credentials I'm using, and it's a bit, for me it's easy, but there's a configuration script here, and again, this isn't important how you do this, but I paste that in there, I save it, and then I can just secure shell SSH into that profile, which is AWS Ohio. Okay, but whatever program you're using to secure shell into it, that's what you need to do. Okay, and boom, I'm on my Ubuntu instance. Now, one last thing, and this is just my my preference. I need to attach. I've got a volume that I always that's a permanent volume that I keep all my programs on. It's called data volume, appropriately named. So I need to attach this to the master so that I can get the Spark program, the Spark Python program off so I can run it. And because I've conveniently named the instances at Spark Master, I know which one I want to attach it to. So now I've attached that to the Spark Master. I'm up here in the Spark Master. So the first thing I'm going to do is I'm going to, and this is kind of a sidebar because this is just part of my workflow. And my attach point is Harvard. And it would help if I spelled SuperDo right. Okay, so I'm mounting it. Okay, so great, that's done. Now, the next thing I want to do is I want to start Spark Master in the background on this instance. To make it easy, I saved the code for that, and it's kind of small here, so I'm going to copy and paste it, but let's see if I can increase this some. Okay, so for the master, it's spark home /bin /spark class Apache spark deploy master, and then run it in the background. And that starts master up. And I'm going to copy that, Control C, come over here, Control V, paste it. Okay, great. Spark master is running there. Now, because I'm not using the scripts that come with Spark, I've got a secure shell into the 3 workers and start Spark worker on each of those. But first things first, I need to come back here, come back to my instances, make sure that I've still got the master's IP address, because when we start the workers, we have to tell them, hey, where is the master at? Okay, and I'm going to replace the last time I ran this with the current IP address. And we'll look at that code here in a second. So the first thing I'm going to do is get the IP address of the first worker. I'm going to copy it just by double-clicking on it, Control C. Now I'm in the Spark Master because of that code that we ran and those keys we generated from learning Spark, and we had set those up previously. I can secure shell into each one just by SSH, Control V to paste the IP address, and then boom, I'm in the first worker. Now I'm copying, and I'm going to zoom in a little bit. I'm copying the code, and I put it in the wrong place, but we'll need it there eventually. That's to actually run the program. So let's come up here and put it in the code to start the worker. Okay, so it's Spark Home, bin class, Spark deploy, yada yada, .worker, and then it's just telling it, hey, here's where the Spark master is, and here's the port. And then again, I'm running this in the background as well. So I'm going to Control C to copy that. I'm going to Control V to paste it. It's running in the background. I can exit out of that worker. Now I've exited out of there. I'm back to the Spark master, and this is just rinse and repeat for the next 2. Copy this IP address, SSH, Control V to paste it. Come back over here, copy the worker, Control V to paste it, exit. Come back here, get the last one. Control C, SSH, Control V. Now this could be automated. I haven't done this because it was a bit beyond the scope of what I wanted to attempt. But this could all also be automated with Boto when you're first starting up the instances. But part of it, I wanted to show everyone how to do this, because if everything's automated, then you really don't learn a whole lot other than, hey, automation's great. But, okay, and I'm going to exit out of here. If I can spell exit correctly. Okay, so now we're back at the master. Now, let's take a look at this. So we've got the master's IP address. And if we go to the website, and this is the old one, so I'm going to paste in the new IP address. And it shows the Spark, and a lot of times it also shows the private IP addresses, so this whole thing isn't fully functional. I don't know why, but it shows, hey, look, we've got 3 workers here. They're alive. They've got 2 cores, and they've got a ton of memory, and nothing's happening. There's no running applications, but we've got 41 gigabytes total, 6 cores total in use. Hey, so that's great. Okay, Now, so our Spark cluster, and let's look at our PowerPoint presentation quickly. This section here, we've just fired up the Spark master and the Spark cluster. Now, the Kinesis stream isn't going yet, and the ioT simulator is not going yet, so that's our next step. So if we go back to our Jupyter program, the next thing is to create the Kinesis stream. We can do this in Python. We can do it in the command line interface or web interface, but this is pretty easy, and so we're going to keep on doing it in Python using Boto 3. We're going to create this with, for me, a fairly large capacity. We're setting it up with 5 shards. So from the AWS documentation, what's a shard? It's a base unit of throughput. We can get 1 megabyte of data a second input, 2 megabytes output. It'll support, each shard will support 1,000 put records per second. So this should support 5,000 messages a second. Okay, so the stream name, very creative, ioT stream 1. The same nomenclature we've seen before, Kinesis client object equals boto3.client. And you'll notice this is the exact same for each one, boto3.client, and then the type of service that you're starting. We'll also use the waiter, and it's going to just wait while the stream exists, and then it'll tell us once it's got the stream provisioned. So we're going to try to create the stream, and it's going to tell us it's waiting, and then it's going to tell us when it's been created, or if the stream already exists, it'll tell us, hey, a stream already exists by that name. And this takes about 10, 15, 20 seconds, so let's go ahead and get that going. And while that's going, let me scroll down here a little bit. The code above creates a stream. The code below is going to create the data that goes into the stream. Our imaginary scenario, we've got couriers which are traveling all over the state. They're picking up packages for delivery, and customers which are pushing buttons saying, hey, I've got 1, 2, or 3 packages to be picked up. Okay, the couriers automatically send telemetry data, which it's going to include their ID, their position, their speed, and any mechanical issues that are applicable. The Internet of Things device automatically sends that. The customers in this world have a button they can press. It creates packages, package pickup request. Okay. Now we look up here. Hey, the stream's been created. If we try to do it a second time, it's not going to crash. It's just going to tell us, hey, a stream by that name already exists. So that's great. Okay, so I want high throughput. I want a whole lot of, be able to create a lot of volume of data. So I've done some experimenting around, and there's a couple of methods to put the data in the stream. One is put record in the stream, and this does it record by record. And the other is put records, and that does 500 up to 500 at a time. So I'm using both. I'm using the 500 at a time method for the telemetry data, and I'm using the 1 at a time method, which still is pretty quick for the customer data. And both of these are functions that so the function is put to stream. It takes a payload, and then it takes the ioT ID, and then the put to streams, which does the batch at 500 at a time, just takes a list of records. So let's initialize both of these functions. Okay, so ideally each courier should automatically send telemetry data every few seconds. We want it random. We don't want the same data every second. So we're going to use a whole lot of random sampling here, and we have a sample size of 30% of our total amount of couriers, because everyone's not going to be checking in like clockwork. Okay, that's not how the real world works, or Internet of Things messages. So we have to have a lot of randomization to keep it somewhat realistic, shall we say. Okay. So this is our courier ioT telemetry function, and this creates the message. It runs a lot of randomization, and then it sends it to the functions above that we just initialized. So first of all, part of our message is going to be whether everything is okay with our device, in this case our courier mobile, or whether there's a maintenance issue and we've just labeled them 1, 2, or 3. They don't necessarily mean anything, but that gives us some kind of something to filter on. And then we've got a lot of randomization, whether it's all this has to add up to 100%, but from 0.002% or from 0.2% to 1.5%. And this is just used to give a distribution for okay, a maintenance problem 1, maintenance problem 2, and maintenance problem 3. Okay, and then each time we're sending a batch of messages, we're going to vary between 15% of our couriers and 45% of our couriers. So we're not always getting 300 or 500 messages every second. So we pick a number between 15 and 45% of our couriers, and then we randomly choose our courier numbers. So we're not getting 100 to 500. It's a random sampling. And again, this is just to keep it realistic. Okay. Where we're going to go now, we have a list of all the couriers that are being sent messages this second or this cycle, and so we have that in a list. It batches up messages 500 at a time because this is the one that uses the batch or send records at a time, and then it creates our message and puts it in a dictionary here. So what's our payload? Okay, well, we've got the courier ID, we've got the topic, we've got the current timestamp, the position, the speed, and equipment status, which will either be OK, 1, 2, or 3. We build a list, and then we put that in the, we call our function put to stream, and we put that list in the variable or the variable records. Okay, that calls this function up here, and that puts those 500 records in the Kinesis stream, and then it starts over. There's a delay here, so it's not running continuously, and that delay varies. It's a sleep time, so that's the frequency, which we're going to call below. And it's, I think the way this is set up now, it's anywhere from like a half second to 2 seconds. So again, there's some randomization. The customer message, it's pretty much the same. There's randomization involved. The takeaway here is there's different information: the customer ID, the topic, timestamp, position. In this case, whether there's what kind of payment they are offering, whether it's cash or credit, and how many packages they want picked up, which is 1, 2, or 3. And all of these are randomized to a certain degree. So again, we're not just getting the same message time and time again. This puts to the stream, and then every time it does this, it keeps a track of how many messages it sends, so we can kind of come back and check and get an idea how many messages we're creating. Okay, so I've been talking. I'm not sure if I've actually run these cells, so let me just go ahead and run these cells again. Now, I'm running these in 2 threads because I want the customer messages to go out and I want the telemetry messages to go out, and I don't want to have to switch back and forth between them. So I just run them in 2 threads, and I let Python figure out the sequencing. So that way both functions are running at the same time. So topic 1 is the topic for the courier, and it's Massachusetts/courier/telemetry, and the frequency for each block of messages is 1.5 seconds. So it's going to vary everywhere from half of that to twice that. So from 0.75 seconds to 3 seconds before it rinses and repeats. Customer pickup, that's not as frequent. So that's going to, so the frequency there is 6 seconds, and again that's going to vary as well. Okay, so we have our thread class here, and we have it's going to run the function that we pass it, and it's going to run the arguments that we pass as well. So we create a couple of threads, thread 1 and thread 2, very creative. The first one, the function is the courier ioT telemetry, and we're passing it the first topic and the first frequency. Second thread, it's the customer ioT function. We're passing it the second topic and the second frequency. We start the threads, and then we start cranking out messages. And what these are doing right now is these are going into the Kinesis stream. We're going to start up Spark now. with the program and process those. Okay, so starting Spark Submit, we've done this before. We need to submit with the package, which is the Kinesis package. So Spark streaming, Kinesis, etc. If we're running Spark in a cluster, we've got to pass it the master argument and give it the actual address of where the master is, as well as 7077 port. We're given each worker 8 gigabytes of memory. Otherwise, it uses, I think a gigabyte or half a gigabyte by default. But each of these machines has over 15 gigabytes of memory, so we're going to go ahead and use that. And then last but not least, I pass it the name of the program I want to run, which is 2-iot filter.py. So I'm going to copy that whole thing. I'm going to paste it. It's going to download everything it needs for the Kinesis package. It's going to go again and check for the table and delete that and make sure that table's been deleted. And then it's going to start processing data. Now, I don't have it putting out a whole lot of information here because this is essentially a filter. What I am interested in is, can Spark keep up with the data that's going into the Kinesis stream? So how far is Spark behind the timestamps there? And so what I do have it print out. I have to do a calculation of the server time, and then it takes it the difference between the timestamp time to see if it's actually falling behind, keeping up, etc. So while this is getting up to the first, starts at the beginning of the stream, and there aren't any messages, so it takes it a few minutes or a few seconds before we first started throwing messages in there. So let's go back here to our Spark web page, and you see we have an application running. And each of the workers is using 8 gigabytes of memory. Okay, so we look here, Spark's 15 seconds behind. Spark is 11 seconds behind. It's keeping up pretty well. And it's filtering these messages. It's putting them in the SQ. It's, the ones that customer request, it filters those out of the stream, puts those in an SQ queue for further analysis or for further actionable items. It also filters out the ones that maintenance has a maintenance of 1, 2, or 3. So now let's look at the visualization. And we've got a couple. We're using D3. It works good sometimes, other times it doesn't work so great. So let's see. Okay, so this is a real-time customer pickup request. So, and this updates every 8 seconds. So Spark is, I think, updating every 10 seconds. And it's taking this, it's writing it to an S3 bucket. This refreshes every 8 seconds, pulls it out of the S3 bucket. And like I said, it's kind of wonky sometimes as far as the screen drawing. And it gives us a real-time visualization over the last few seconds or minutes, however long it runs, of how many pickup requests there have been. Like at this time there's 48. Previously there were 114. And like I said, it gets kind of wonky sometimes, so I'm going to let this run for a couple of minutes. The second visualization I have is a geoplot of the couriers that are having maintenance issues. let's try this, and well, here we go. And these are plotted all over the state. It gives the information, and then it updates as we get new couriers with maintenance issues. And then they're color-coded depending upon whether it's maintenance issue 1, 2, or 3. Okay, so this is actually working pretty well. Let's go back to this visualization. And I'm going to let it run for a few minutes, and let's go back and look at Spark. So Spark is 6 seconds behind the data stream, 8 seconds behind the data stream, 10 seconds. So it's doing a great job keeping up, and especially if you look at how many messages that we've sent. Right now I have approximately 136,000 messages, and that's over the course of the last 5 or 6 minutes. So it's doing a pretty darn good job. Okay, so now we have some more data, and it looks like it's kind of finally settling down and graphing the total pickup request. Well, spoke too soon. Okay, so enough of that. Okay. When we're done, all we have to do is kill Spark. So Control C. Okay. I'm going to start breaking down the infrastructure. So the first thing I'm going to do is unmount my external volume. I'm going to exit out of here. And then let's go back and let's kill our ioT simulator. So it checks for exit flag of 1. So if we just run this cell with exit flag of 1, we'll kill both threads. And sometimes it takes a few minutes, but there's the first thread that's dead and the second thread. Okay. Now everything we've still got our Amazon resources provisioned, so we're going to clean those up. So if we come down here and run this cell, this is just like above, except we're saying, hey, get the EC2 instances I have running, and get their names and terminate them. So we'll run this, and let's go over here real quick. Do a refresh, and we can see the instances are shutting down. It's very quick. Now we're going to delete the Kinesis stream and the data because we're paying for it, or I'm paying for it, and I don't really want to pay to store all those messages. So the same thing, give it the stream name, we create the client, we can probably use the same client name, and get the waiter to wait, and it takes a while, 10-15 seconds, and then once it's deleted, it's going to say, hey, it's deleted. The next thing we're going to do after that is deleted is create the DynamoDB table that's used by Spark. And we don't really have to create that table. Spark creates it. It's just a matter of us deleting it on cleanup. So it says the stream's been deleted. Just like before, if we try to delete it and it's already been deleted, it's going to tell us, hey, you've got the wrong name, or that stream is gone. Housekeeping, get rid of this table that Spark was using to keep track of its place. And delete the simple queue service queue. Okay, and so our instances are terminated. And if we want to check briefly, for Kinesis. I've got no queues there, or streams. If we refresh our Spark Master, it doesn't connect because there's nothing there. Okay, so the last bit of code is the code that runs Spark itself. We import standard imports along with JSON and Boto 3. The Spark standard imports. We don't need to set our AWS keys in the environment because we're using that IAM instance that we looked at before, but I do set a lot of constants here. The region, the queue name, which is io2 queue FIFO that we talked about before, the app name, which is io2 prototype, the S3 path, which is where we're storing our visualization data, and the S3 bucket name, the S3 file name, stream name, and the endpoint URL, which we need for Kinesis. And the checkpoint interval, this is what Spark uses to write to the database table every 2 seconds. And just like we saw in Jupyter Notebook, we're going to set up a few things. We're setting up our SQS client to send messages to this queue. We didn't look at that, but we're dumping a lot of messages in there. And this is essentially, hey, we filtered stuff out. We're queuing it up for the next app to work on. And the next app will read that and act on it, however that app appropriately. Okay, the DynamoDB setup. So just like before, we're not setting up the table, we're deleting the table. We've deleted it twice other times, but again, we're making sure that this table doesn't exist because it will throw an error if Spark tries to use a table that comes from a previous stream. And then we just set up the S3 client with the region name, which is the US East 2. Okay, all that's said and done. Now we're getting down to the Spark code that we know and love. Very important, if you're running this on a cluster, don't set your configuration or conf with the .setMaster local. Okay, leave that out. It's just sparkconf.setAppName, because if you have set master local, even though on the command line, if you ran it as a cluster, this will override that, and you don't want that. Okay. Lines equal Kinesis util. This is what we use to actually read the Kinesis stream. We map these, then we get a dstream device for Spark streaming. I'm going to cache that device because I'm going to use it for a couple of filtering things, and I don't want to have to read it twice. If I read it twice, I'm going to get different information. So I cache that, and then I use it to filter for, first, the courier maintenance issues, and then 2, the customer pickups. So cache once, use many times. I've got a function here to process. Okay, so first of all, let me go back up here. So I've got that stream cached. So the first thing I'm doing is Kinesis isn't a publish subscribe data stream. So I've got to filter out of there. So I'm looking for topics that equal Massachusetts, courier, telemetry. And I'm going to filter that where the equipment is not okay. I'm looking for this. This is where I'm picking the nuggets of information out of the thousands of pieces of noise out there. So I'm assigning that to equipment data. For customer pickup, I'm not looking for anything specifically other than the topic is Massachusetts customer pickup. So that's assigned equipment data and customer pickup. Got 2 functions here. The first one is to process the equipment. Okay, takes an RDD, assigns it to the variable data 0, and we create a basically we're going to create a JSON message. Data equals JSON dumps, so we're doing a key value, and then we're going to print the total filtered maintenance messages this round. Okay. If the length of the data is greater than 0, we're going to send this to our SQS queue, or that's redundant, SQS. If it's not greater than 0, we don't have any, so there's no reason to call this. And finally, what we're going to do is we're going to output some data to S3 for our visualization. And this is the coordinates that we saw. and this is what we were using up here to get the key value pairs out. Okay. Same thing for the customer, less filtering there, but pretty much the same idea. We are doing a count of the customers, and while we're doing that, I put in here, hey, let's do some math and see if Spark is keeping up with the data stream or not based upon the latest timestamp we got from the message. Okay. And then again, if we're going to go ahead and send a package customer pickup request and put that in the SQ as well. And then finally, we're going to go ahead and put that in S3. Okay, so that's our actual Spark program. Let's go back to, and actually let me go over here real quickly. So that writes to S3, and then S3 you can run a small web server, so it gets the information out of there and runs those kind of unreliable visualizations, and then we can look at those there. Okay, we've talked about the technology, we've talked about the data set. So my lessons learned. We probably created, I don't know, but we're at 100,000, 100+ messages. Spark and Kinesis had no issues keeping up. They were within pretty much real time. What I learned and what I didn't anticipate was the software development kit is a really big help doing this, and I'm a big fan of it now, because you're able to tear up or build up and tear down resources very quickly. A lot like the command line interface, only it runs on Python, so it's saved a ton of hours. We're mixing ecosystems here because we're using Spark with Kinesis. There's things in AWS that you could replace Spark with. I don't know if they're better, but they would work together better. Same thing probably if you're using a different cloud services such as Google or Azure. In the future, I would just choose one ecosystem and keep everything together, because they're designed to work together better. IAM profiles are great because now I don't have to pass credentials. I just set the IAM profile for the instance, and then my program has access to whatever rights I've given to that. Start small and build slowly. There's an ioT service, Internet of Things service, and Amazon Web Services that pretty much does everything you need for ioT. I don't understand all of it, so I like to start with the basics, and then as I understand more, probably start incorporating more of those devices. The same thing that goes for Spark. There's Elastic MapReduce. It has Spark. It also has a lot of other things on there I don't understand, so this was pretty simple. Use the Spark that we know and love, that we've used for the whole semester, and only run it on just a couple of extra clusters or a couple of extra instances, and see how it works there. And this way, help me understand it more. Learning point, but the literature isn't always correct. The way it told me to run start up a cluster didn't work for me. That's why we had to go into each one and start it manually. And there's various websites that tell you how to run Spark on an EC2 cluster. None of those worked. This worked for me. Okay. It wouldn't work if I was doing more than 3 or 4. It'd be a real pain, but for this, it works pretty well. My security profile, as I talked about, was wide open. Don't do this unless it's an academic exercise, because it's just bad. Okay, so start less secure, and then after you know what's going on, go ahead and start securing things down. Last thing is the cloud services, and it's not just AWS, I suspect, but all cloud services can be cheap if you're flexible. This whole project probably cost me less than $2 from beginning to